So, very good afternoon to one and all. Uh, So, before I proceed, I would like you to know this is the online live interaction for the NPTEL course that is on mass transfer operation ones. So, before you proceed for the week two session for this live interaction, I would like to know the students who have joined this class for the first time. Is there anyone who have joined this class for the first time, like the live interaction with me, or they have joined all the previous two classes? Yeah, please go ahead. You can speak out, that's not a problem. So assume that you guys have gone through the week 0 and week 1 uh, videos that I've uploaded on YouTube. It's just the basic things of mass transfer, nothing more in that. So from today we will start actually solving some of the numericals that has been already been taught in the NPTEL online lectures, as well as some of the like one or two more questions related to the basics one. Uh, okay, so we'll start. Just a minute. So I'm seeing so many students from like same role, like same colleges actually. Can anyone speak out? Like 9CH, 11CH, 13CH, 18CH. So you're all chemical engineers, I assume so. Okay, not a problem. We'll proceed then. So, a very good afternoon. Welcome you all students from this online live interaction on NPTEL online course certification. That is a course on mass transfer operation 1. So this is one of the basic fundamental courses for the chemical engineering undergraduate students, and this course has been offered by. Sorry. So this course has been offered by on NPTEL by Professor Vishnu Pada Mandal, who is a professor in the Department of Chemical Engineering at IIT Guwahati. And little bit about myself. I will be the teaching assistant for this course, like I've been saying from the past 2 weeks. So a little bit about myself is that I am Raspu Shubham Ajit Kumar, and I am a PMR scholar in the Department of Chemical Engineering at Indian Institute of Technology Madras. So we will be taking like myself, I will be taking all the live interaction sessions of this course on NPTEL. That is from July till I think October and November. So we'll be meeting up every weekend, that is on every Saturday, and that too in the noon session from 3 to 4 for the live interactive sessions in order to solve some tutorial assignment problems and some of the basic fundamental topics that has been covered during the entire week. So we'll go through what has been covered during the entire week on NPTEL, some related numericals and solutions for that I'll try to solve out during this live interaction. And in between, if you have any issues or problems related to the assignment problems, but I will be able to solve only that assignment problems once the due date has been ended. I will not able to solve the entire solution problem here, since week 1 and week 2 assignments problem are still there to be ended. Once it is ended, we will try to solve out all each and every numerical questions on this live interaction. So at that time, you can ask your questions which you might have get got like uh, deducted your marks during the assignment solutions. So before proceeding for the week two, like in week 0 and week 1, we started with what is mass transfer, laws of mass transfer, that is Fick's first law, Fick's second law, and some basic fundamental concepts of mass transfer and how it different from the heat transfer also, and some basic terminologies like hydrothermal, isotherms, and like I said, isobaric, isochoric, isotherm. What are the different terms and how they can relate it to the mass transfer also at a later point of time. So during this week two, as per the NPTEL SWAYAM portal content, these all are the four topics that has been already been covered. So this is one, two, three, four. So there are four different topics, and I presume that all of you guys have might have gone through the week two contents already, because this includes some of the derivations for like diffusion to variable cross-section area, and similarly for the gas diffusion coefficients. So this variable cross-section area, it might be through a convict or a sphere, or in examinations also they as far as NPTEL is concerned, they will ask the same things like through the what has been taught in the class. But apart from this, if some of you are going to get giving the examination of this gate, that is graduate apprentice training exam, so it will be better if you go to like some of the different cross section areas, different cross section segments of the materials, say sphere, rectangular, triangular. The only thing is that you need to derive the formulas, nothing else. But the basic thing is that if you see the concepts of convict as well as the sphere, all things remain the same. Only thing is that you need to change the diameter, radius, area, volume, and you can derive your own equations as well as. So this week has been like the diffusion of gas phase, the diffusion coefficients, and multi-component diffusivity. So like last week I said there is a diffusion of A, so non-diffusion B, and equimolar counter diffusion. I didn't mention the formulas for that because I just mentioned that Na, Nb, J, Jb, that are the molar and the molar flux is related to fixed location in the space and average molar velocities flux actually. So, sorry. So before proceeding, I will just mention what is like. I know that some of you guys might already went to the course lectures, but if not, then it's beneficiary for you also. The first one I will mention, that is a steady state diffusion of A through non-diffusing B. So like I said, there are two different fluxes, Na and Nb. So here you can consider the absorption of the gas molecules from the atmosphere, or consider absorption of the ammonia from the air into the water. So you can consider ammonia has been absorbed and the air is not absorbed, but it's being absorbed in the water. So Nb is the water. So you can say if B is constant, that is non-diffusing B, that is water is not diffusing, you can taken at zero, and you can say that the constant diffusion of A. So we can say that Na upon Na plus and b equal to 1. So this term basically arises from a mathematical derivation. There is nothing much more. If you want to go in the deep fundamentals, how this has been arrived, you have to go to the like various derivations. But here we have been mentioned it directly. So what I've been saying is that if you want to solve some of the numerical questions at a later point of time, just 1 minute, guys. One. I thought someone else. Okay, okay. Sorry guys, I was just there in between. So the thing is that, like I said, for this the basic derivations that Na upon Na plus Nb, you have to derive to the mathematical expressions. But if I solve it directly, you can mention if you have seen these formulas, that is dAb, that is diffusivity of A respect to B upon RTZ ln of Pt minus Pa2. Similarly, Pt minus PA1. And you can also mention this in terms of the component B, that is PBLN, that is the logarithmic ratio, or you can also write this as Na is equal to DAB into PT RTZ, and this is PBLN. I will mention you guys what is PBLN also. So this you might have already went through the lecture notes or the NPTEL online course certification course, because they have directly mentioned, and this is one of the basic fundamental equation uh, you might be using during the examinations also, because they will give you diffusivity and the partial pressure of A or partial pressure of B, and they need to determine the molar flux of A with respect to B. Indirectly, they will also ask you what is partial pressure of A if they give all the data to you. So this is what for diffusion of A to non-diffusing B. Similarly, we have equimolar counter diffusion. So we can say Na and Nb are diffusing equally. So Na equal to minus Nb. And for this, the flux of A can be written as DAB RTZ PA1 minus PA2. Okay, so these are some of the things that you might have to remember, because these equations may be directly being used in the examinations also. So that's why I'm just mentioning the basic equations for diffusion of A to non-diffusion B and equimolar counter diffusion. Apart from that, we have also seen this multi-component diffusion in components. So steady state diffusion, in multi-component mixtures. Fonts are not clear. Okay, what I'm writing is not clear or fonts are not clear. Okay, I'll try to clear it out. So for the multi-component diffusions also, you have seen that diffusion of A with respect to the M is equal to 1 minus. So I'm writing just the formulas directly because I don't want to derive. I can also derive it, but it will take much longer. It will take the entire one or for one equation to derive, because you have to go through the deep fundamentals and derive it again from the scratch actually. Summation I equal to N yi upon dAI. That's the diffusivity of the species I. So these three are the equations for diffusivity, and how to derive this is somewhat. I'm not going to tell you guys now, because on the basis of this, there are so many numericals directly been asked in the gate examinations as well in the NPTEL also. So, and there is similar diffusivity for the liquids also, like for the steady state diffusion of A to non-diffusion B in liquids. These are just for the gases what I mentioned right now. So before going it directly, we'll just try to solve out some of the numericals on the basis. Before that, I will just a quick question, like 1 mark questions. So the molar average velocity of the components in binary mixture in which there are equimolar counter diffusion is. So like I just mentioned the equations previously. So this is one of the equations that has been asked in the assignments also. So can you pick out the correct answer from this one? So there are two different components which are a binary, which form some binary mixture, and in which they are equimolar counter diffusion. So what is the molar average velocity? So there are two different types of velocity, that is mass average velocity and molar average velocity. What have been asked here is what is the molar average velocity in a component of binary mixture which they forms equimolar counter diffusion. So if you say two different components, so that is A and B, and the flux of A will be Na and the flux of B will be Nb. And for the equimolar counter diffusion, if you see Na equal to minus Nb, therefore Na plus Nb equal to 0. So what is the correct answer for this? That is the molar average velocity. It's simply nothing but 0 actually. That's nothing more to search for. So only thing is need to know what are these equations and how they can be related directly. So this is just like a quick view, because I mentioned the equations. I wanted you guys to know how you can relate the equations with this one also. I've not mentioned regarding any partial pressure or anything here. So this is one of the questions that I've taken from the book directly. This is the reference book, and I wanted you guys to go through the question what have been given here. So it's like based on this steady state diffusion, that is diffusion of A to non-diffusion B and equimolar counter diffusions equations, and the week two contents, week one contents that I've mentioned in the last class. So you can see is, so oxygen A is diffusing through carbon monoxide, that is B. So we can just write down what is A, what is B. And this is carbon monoxide. Under steady state conditions. So the condition has been given as steady state. with the carbon monoxide non-diffusing. So B is non-diffusing, A is diffusing. Okay, so the total pressure is given as 1 into 10 square Newton per meter square. So total pressure we will write it as 1 into 10 is to 5 Newton per meter square, and the temperature is 0 degrees Celsius. The partial pressure of oxygen at the two planes are this and this respectively. So what has been given to us is the partial pressure, that is a distance of 2 mm. So Z is, if you get taken in meter, so 1 meter is equal to 1000 mm. So this will be like, and you are a 0.002 meter. Okay, and what are different things? There are two different partial pressures, that is PA1 and PA2 are given. So PA1, PA2. So PA1 will be 13,000 Newton per meter square and 6,500 Newton per meter square. The diffusivity of the mixture, that is DAB, diffusivity coefficient is 1.87 into 10 is to minus 5 meter square per second. Calculate the rate of diffusion of oxygen in kilomole per second through square meter of the two planes. Okay, so PA1, PA2 we have. Similarly, you can derive the through the equation, that is diffusion of A to non-diffusion B. So we can write the equation first, that is diffusion of A. So the molar flux of A can be written as DAB PT RTZ PBLM into partial pressure of A minus partial pressure of B. Now PA1 plus PA2 is equal to PT. So you can have PA1, we have PA2, and we have PT also. So you can determine PB1 and PB2. Therefore, PA1 plus PB1 equal to PT. So PA1 has been given us to us as 13,000. Okay, plus PB1 equal to, and total pressure has been given to us as 10 is to 5, and the units are same, that is in Newton per meter square. This is also in Newton per meter square. So from this you get PB1 equal to 10 is to 5 minus, you can write it as 13 into 10 is to 3. Therefore PB1 equal to, if you calculate it, it might come as 10 is to minus 5, 10 is to minus 10 is to minus 2, and this is somewhat, yeah, 87 into 10 is to 3. Okay, similarly we can determine PB2, that is PA2 plus PB2 equal to PT, because the total pressure is the sum of the partial pressure of the components involved in the system. Okay, sorry. Therefore PB2 similarly determine therefore PB2 equal to 10 is to 5. What is P2? That is 6500. Therefore 6.5 into 10 is to 3. Therefore PB2. So these are all the partial pressures actually. So PB2 will come about 6.5 to 10. So this is 10 is to 3 and 10 is to 5. So 93.5 into 10 is to 3. Okay, now all we have to do is to put all the values that has been given here, that is PB1, PB2, directly into this equation. So PBLN is indirectly, like you can write it as logarithmic difference, that is PB2 minus PB1 divided by ln of PB2 by PB1. So this is the logarithmic pressure difference, and from that you can directly put the equation. So we will get Na equal to DAB. So DAB we have is 1.87 into 10 is to minus 5 DAB into PT. PT is given as 10 is to 5 Newton per meter square. DAB into PT, and we have PA1 minus PA2. PA1 we knows and PA2 we also knows. That is 13 into 10 is to 3 minus 6500, that is 6.5 into 10 is to 3. Okay, divide by RT, that is R is a universal gas constant, 8.3151 joule per mole Kelvin. So 8.31451, and the temperature is given as 0 degrees Celsius, so we can consider it in Kelvin because we have taken R as joule per mole Kelvin, so the temperature is 0 degree Celsius, so I am taking it as 273 Kelvin, 273.15 Kelvin into, that is PBLN. So PBLN, if you find out from this formula and put all the values here, that is PB1, PB2 and PT, you will find it out as 90.2 into 10 is to 3. So by solving all these parameters, we will get that what has been asked in the question, that is molar flux of A in the solution, that is 2.97 into 10 is to minus 5 kilomole per meter square per second. So this is the final answer. So this is one of the basic like terms that can be asked directly into the NPTEL examinations, plus in the GATE examination also. Nothing I have done here is just we have taken all the parameters value that has been mentioned and we are directly solving the equations. Similarly, the same question can also be solved through the equimolar counter diffusion also. The only thing is that in that case we will take Na plus Na equal to minus Nb, and with there is a different formula for molar flux of air, that is DAB upon RTZ and Pa1 minus Pa2. So this is the only difference between that diffusion of A to non-diffusion B. That is, in that case, one is constant and other is diffusing. Where in the other case, both are diffusing with equimolar proportion. So this is another simple one. And this is second question, and this is the question one. So first we write out what has been given. So this is also has been taken from the reference book, that is Mass Transfer Operations by Robert Whitehead. So what they've been asked specifically is that recalculate the rate of diffusion of oxygen A. So just write out what is the component A, that is oxygen. In the above equation, assuming that the non-diffusing gas is the mixture of methane and hydrogen. So B and C consists of non-diffusing gases. Okay, and the ratio is given as 2:1. So the B, that is methane, is present in 20% and the hydrogen can be considered as in 10%. It is 2:1. So the diffusities are estimated to be this. So these are multi-component gas mixtures. You can easily determine what has been given to you. So the diffusivity of O2 with respect to H2 is given as 6.99 to 10 is to minus 5, and diffusivity of O2 with respect to methane 1.86 into 10 is to minus 5, and both the units are in meter square per second. Okay, so what they have to determine is the rate of diffusion of A. So if you consider diffusion of A to the multi-component mixture, we have this formula that I have written previously. Because there are two component gases that has been given, so we'll write the diffusion of A respect to B and diffusion of A respect to C. So Y dash B, that is the molar composition of B. So previously we all yeah, so before proceeding to this, we have to determine the values of YB and YC here. That is the more fraction composition of the gases in, that is the A respect to the B. So all the things are the same. The only thing is that you need to determine the YB dash and YC dash. So if we take YB dash and we have given the molar composition, that is B respect to C equal to 2:1. So YB dash will be 2 upon 2 plus 1, that is equal to 0.667. Similarly, yc dash equal to 1 upon 1 plus 2 equal to 0.333, or you can directly write it as yc dash equal to 1 minus yb dash equal to 1 minus 0.667 equal to 0.333, because the total molar fraction will be equal to the sum of one, that is yb dash plus yc dash must be equal to 1. So you can see this is 0.667 plus 0.333 will be equal to 1. So we are correct here. So just directly placing these values of yb dash and yc dash, 0.667 divided by diffusivity of A respectively, that is given as 1.86 to 10 is to minus 5, plus this is one parameter, that is this, and the other one is given as 0.333 into diffusivity of second one, that is 6.99 to 10 is to minus 5. So the only thing is that if you solve the above equation, the diffusivity of A with respect to the multi-component mixture will comes out to be 2.46 into 10 is to minus 5 meter square per second. So this is for the multi-component gases. Okay, so what we have seen here is that there are two different gases, methane and hydrogen. They are not diffusing, and we have to find out the diffusion of A. Previously it was diffusion of A to non-diffusion B, but here there are two different gases, so we have to find out the diffusion of A with respect to the multi-component gas mixture that are not diffusing. So what we have done is that we have taken the formula that we have derived from multi-component gas mixture. I'll just show you that formula. Previously I have also mentioned. So this is like that formula. Okay, multi-component gas mixtures. So we have applied the same thing here, that is this one, 1 upon molar fraction of species I with respect to the diffusivity of A with respect to the species I, that is yi dash upon dai dash. So I applied the same formula here, and you can see 1 upon yi dash by dab, because there are two different gases which are not diffusing. We have taken yb and yc, and you have taken the diffusivity of A with respect to the two different gases, that is B and C, that are not diffusing, and we have recalculated, and we have calculated mole fraction of B and C according to the volume ratio that is given to us, is that is 2:1. So yb dash should be 2 upon 2 plus 1, and yc dash can be 1 minus yb dash, because both the mole fraction must be equal to be 1. Okay, so these are some of the things, and here we need to calculate the Na first of all, because only thing we have calculated diffusivity, because diffusivity was not given in the here in the question directly. So just we have to place this diffusivity and directly do all the calculations, same thing again, like Na equal to dab pt rtz pblm into p1 minus p2. So the diffusivity here changes to be 2.46 into 10 is to minus 5 into pt was given as 10 is to 5. That is from the question 1 itself. R is 8.31451. Temperature is given as 0 degrees Celsius, that is 273 Kelvin. PBLM we have already found it out through the logarithmic temperature difference, and it came out to be, so I'll just show you where is PB. Yeah, so PB1 and PB2 we found it out here, and similarly we find out the PBLM values, and we have mentioned it here also that sorry, so this is the PBLM value using the logarithmic pressure difference, that is it came out to be okay, so the distance I have not mentioned. So this is RTZ. Z is also there, right? So it's like 2 mm. So we'll convert into meter. So 0.002. And what is PB value? 19.2 into 10 is to 3. And PA1 and PA2 are already given. That is 13 and minus 13. What is PB? Yeah, here. This is PA1 and PA2. So 13 minus 6500. Okay, so just solve this, you will get the answer directly. So this is one form of question that you can solve if multi-component gas mixtures are given, so you can determine the diffusivity of A with respect to the multi-component gases that are not diffusing, and you can take the diffusivity of A with respect to the multi-component gas mixtures and can use these equations if they ask diffusion of A to non-diffusion B, and if there is equimolar counter diffusion, you can use the different formula. So this will comes to be about 3.91 into 10 is to minus 5 kilomole per meter square into second. So you can compare this flux, that is 3.91, with this one, that is 2.97. This is with respect to only one gases, where in the case of multi-component gas mixtures we get like 3.9, that is much lower value as compared to that. Okay, sorry. So this is another uh, question, and this might has already been given in the NPTEL online lectures, but I wanted to just try it out here also, because these are some of the concepts which like has not been directly been given in the reference books or somewhere else, but it's very well taught by the Professor Mandal on the NPTEL course. So I just wanted to give it a try, just like how these students will understand this like diffusion of it to like various cross-sectional areas. So this one is for the conduit. Similar is there for the sphere also and various other cross-sectional areas on the NPTEL portal. So we'll try to solve this out. So first we'll mention what has been given in the question first of all, because it's better to list out all the things that has been given in the question and then try to solve it out within the basis of the concepts you guys know. So it's better to gain like in-depth knowledge of all the concepts first of all, the formulas that has been mentioned and what these formulas are being used specifically for which questions. So as you can see in this question, what they've given is that the diffusion of CO2, the CO2 is diffusing through non-diffusing N2 at steady state in conduit. So before I proceed with this question, I will just, yeah. So there is some figure somewhat like this. I'm not able to draw correctly here, but if you like conduit, if you can consider the cross section area, okay. So we can take this as position 1 and this as position 2 and this is along the x direction. And you can take the area, that is the width of this is as A1, and this is width at A2. So this is considered as a tapered geometry or a conduit. So what I can say is the A diffusing to the non-diffusing B. So area you can written as half into length into breadth, or you can consider it as a rectangular side, so half into length into altitude. Okay, so there is a derivation for this one also, and it's already been given in the NPTEL portal. I'm not going to solve, but only thing I will write the final equation what they have derived for this, and that comes out to be, that is diffusion of A to non-diffusion B. If you consider is root 3. So this is the same thing. The only thing is it's diffusing through a different cross-sectional area. So that's you have to derive through the basic concepts. Like I solved it for diffusion of A to non-diffusion B, and this is for the same thing but through a different cross-section area, that is through a conduit. So it comes out to be T minus PA. So this has to be 2 and this has to be 1. So this is the formula for the diffusion of A to non-diffusion B through a different cross-section area, that is to the conduit. Okay, now we'll proceed to the question that has been asked here. So we'll see the CO2 is diffusing through the non-diffusing N2 at a steady state in a conduit of 2 meter long at 300 Kelvin. So the length is given, that is 2 meter. The temperature is at 3 Kelvin, that is above room temperature. And a total pressure of 1 atmosphere, that is 1.101325 Pascal. So the partial pressure of CO2 at the left end is 20 kilopascal and 5 kilopascal at the other. So the two different ends, and their pressure has been given, that is P1 and P2 at both the cross sections of the conduit. So the cross section area of the conduit is in the shape of an equilateral triangle, being this, that is point 0. So this is somewhat like 0.0025 meter at the left, and the tapering uniform to the 0.05. So you can consider this one as lower end and this one is higher end. That is a tapered conduit. So this is 0.05 and this one is 0.0025 at the right end. Calculate the rate of transport of CO2. The diffusivity is given as 2 into 10 to minus 5 meters square per second. So we need to determine the rate of transport of CO2. That is the flux. So this question has already been solved in the or during the online this is lecture videos. So it's just basic. You have to write up all the things and the things you have to sort out. Just 1 minute, guys. So what we'll do, we will first write all the things that has been given. So first thing is that we need diffusivity. So diffusivity has been given as 2 into 10 to minus 5 meters square per second. Similarly, what else we look at DAB, RTZ. So universal gas constant will be 8.314 joule per mole Kelvin. Or you can also write it in meters square pascal. That is 8314 meter cube into pascal per kilomole into Kelvin. So this is a different form of the R, that is in meter square pascal. You can also write in meter square atmosphere, that is 0.0823. Different values are there for the R, but we will take consider what all the units are there in the question, given in the question, and we'll write according to that. Temperature has been mentioned at above room temperature, that is 300 Kelvin. Partial pressure at one side is given as 20 kPa, that is kilopascal. So we'll write this in pascal, that is 10 is to 3 pascal, because here the unit is in pascal. Similarly, on the other side, the partial pressure is 5 kPa. So we write it as 5 into 10 is to 3 pascal. Now the cross-sectional width that is given as E1 side is 0.025 meter and E2 is 0.05 meter. So these things are already been mentioned here, like I said. Okay. So this is 0.025 and 0.05. So all the things that are mentioned, we are just writing it down. And the thing is, the difference between the two conduit areas, that is from one end to another end, or the distance is 2 meter. So this is distance between the 2 meter, that is this one, this area. So this comes out to be 2 meter. Okay. Now we will use directly the formula for this cross-sectional area that I mentioned previously here. That is Na is equal to root 3 into DAB PT upon 4 RT A1 A2 X2. So all the things are given here. So only thing is you to determine is the value of the Na directly. So if you know the different cross-sectional areas and the formulas, just you have to write it down. Just before writing it down, just go through what has been mentioned in the question. So you can see there is a conduit term here. I will just try to find out that one. Yeah, conduit. So similar, if you can say, instead of conduit there will be sphere. So according to that, the different questions will be there. So there also you will be able to determine the diffusivity also, flux also, various other terms also. In some of the cases, what they will do is that they will give the molar flux value of A and they will ask you to determine the value of DEB. Similarly, they will ask you to determine the partial pressure of A or partial pressure of B. That is a this is for the steady state diffusion of A to non-diffusion B. Similarly, there will be for the equimolar counter diffusion, the formulas will be different. So from the one basic term, like I mentioned in the first class, second class, and the third class also, I'm mentioning the same diffusion of A to non-diffusion B and equimolar counter diffusion and multi-component gas mixtures. There are many different terms. which can be derived using the same basic concepts of fundamentals that has been mentioned in the lecture notes in NPTEL portal. So I'm doing nothing, just I'm taking the same concepts and trying to solve out some of the numerical problems. So we will write it out what has been given. Okay, so the thing is, it will take a bigger space, so I will write it up uh, here only. Chalo. So Na, so we have root 3 into DAB into PT. So differentiate will be given as 2 into 10 is to minus 5. This is in meter square per second. So we have written root 3 dB. Total pressure has been given it to us. So the total pressure, if you can see, is given to us as 1 atmosphere. I'll change the color so you can see it. So the total pressure is 1 atmosphere. Okay, here you can see it clearly. So 1 atmosphere is, sorry guys, just yeah. So 1 atmosphere you can return as Pascal, that is 10 is to 3 Pascal. So we can, so 1 atmosphere is 101,325 Pascal. So we can write it as into 101.325. This is in kilopascal. So in terms of kilopascal, it will be 10 to 3 Pascal. Okay. Oh, sorry. Yeah. So this is what you have written is root 3 dB into PT divided by 4 RT. R will be, that is what we mentioned is 8314, because I am mentioning this term in terms of Pascal, that is in meter cube into Pascal divided by kilomole into Kelvin. I've taken this value at 314 because yeah, because we have taken pressure in terms of Pascal. So if you want to take, if the pressure is not there, we can take 8.314 joule per mole Kelvin also. But the thing is, we want to keep all the units in a same configuration so that it is easily to derive at one particular answer. 4R and T, that is the temperature has been given to us as 300 Kelvin into the distance, that is Z, that is 2 meter between contact A1 and A2. And the final thing is arrived, so we just said E1 E2 upon x2 minus x1 ln of pt. So yeah, okay. So ln, what is given as pt? Pt is given as 1 atmosphere, that is 101.325 into 10 is to 3 Pascal, and P1 and P2 has been given to us, that is already been mentioned. I've written here also, yeah, that's 20 and 5. So we can write it as 101.3 into 10 is to 3 Pascal minus 5 into 10 is to 3, that is Pascal. 101.3 into 10 is to 3 minus, that is PA1, that is 20 into 10 is to minus 10 is to minus 3. So just solve out this entire equation using the scientific calculators, because in examination also they will provide you the scientific calculators and all the things, so you can solve it out easily using all the cases. So the thing is that we have done here for the convict, that is from the one end to the another end, and how this flow is happening. And since all the parameters are given, it's very easy to just remind the equations. Or even if you don't remember the equation, that's the only thing left is that you have to derive the equations if you know the basic concepts of this diffusivity of A respect to B and through non-diffusion B. So it's better to yeah, it's there. Just one. So it's better to know the basic concepts, because what I'm trying to, before starting the class, I would like to write all the equations that we are going to use through the session. because it might help you guys to need to remember the same equations again and again, because at the end, at last, is method is the final examinations only. So that's what we are trying to solve it out. There are many more equations to come. These are just the basic starting of this mass transfer operation course, because this course is very deep and many more things are yet to come. I will not say it's being scared, but it's better to learn from the starting itself, because if you try to revise each and everything again and again through weeks after weeks, the same concepts, and try to solve out the various different formulas, using the formulas and the equations, it will be better for you guys to arrive for the betterment of your for the final examinations only. So similarly for this, what I've solved is for the convict. You can solve it for the spherical shapes also, as well as for the rectangular, triangular, whatever you want. You can just derive the equations by taking the basic concepts. Or even if you don't want to derive the basic equations, you just have to remember what has been asked in the question. If it's a rectangular or a spherical shape, then you must have to remember where the spherical shape formulas came to and what are the different parameters. So in the spherical shape formulas, there will be radius, diameters, R2 minus R1, and many more things will come out. That the diffusion of A to non-diffusion B, there will be radial distance between them, and the radius and the diameter for the spherical shape, as well as the volume for the sphere. So these are the different parameters. So from taking that into mind, you can determine the formulas, and if you know formulas very well, then it's very easy for anyone to solve out the equations. So for finding this answer by solving all this in one go, even it's better to put all things in a scientific calculator and solve it one time. If it's difficult, try to solve in two different parts. First solve this part and then try to solve out this whole part secondly. So if you try to solve it out, you will get answer as, so this is what we have. Okay, so this is what I have for today. That is for the week 2. There are I have to solve like another 2 to 3 problems also, but I've not shown up here because for that, before proceeding to that, I wanted you guys to solve some of the basic fundamentals problems, because last week I've just shown the equations for diffusivity of A with respect to B, but I've never solved these equations and the questions for what has been mentioned in the lecture notes as well as in the NPTEL portal. So from the next week, what we'll do is that we will try to solve out some of the equations for the multi-component gas mixtures, which involves much more complexity, what which have not been covered in this session. Uh, Apart from that, we will see some of the diffusivity in liquids also and try to solve out their equations. And I think so from the next week, week 1 assignments will be over. So I will try to incorporate all the questions from the week 1, and we'll try to solve it out one by one, because week 1 and week 2 are the basic fundamental assignment questions. From week 3, week 4, they'll start the deep fundamentals on the mass transfer operation. And as we proceed through the course, we'll be able to try to solve out each and everything one by one. So this is what I have for today, and thank you so much for attending this online live interaction. If any one of you have any problem, just let me know right now for the assignments, because I'm not solving the assignment problems because its due date has not been ended. So it's better for you guys to solve it out on your own. If you face any difficulty, just let me know through the NPTEL Swam portal forum, or you can send a mail to the NPTEL team also if you are facing issues with anything related to the course or the registration, anything, you can send a mail to the NPTEL team. What we will do in the next week, we'll meet up next Saturday at the same time, 3 to 4, for solving some of the equations questions. So this today what I've did is that I've taken the questions directly from the reference books that has been mentioned in NPTEL portal, that is Trival. I wanted to include some like simulations, but I can't include in these questions because it's just like the basic things of what I've been doing. So from next week, I'll try to solve out all the concepts of like diffusivity in liquids and the other things that I want to carry out forward. So if anyone wants to have any questions, they can ask right now. If there is no question, we'll meet up next week at the same time, that is Saturday 3 to 4. Thank you guys.